Hi everyone, Dr. Mitch Cox here. Thanks very much for coming to see my talk. A few of you might remember me from a few years ago when I was here presenting as a student under the supervision of Professor Andrew Forbes. But what I've done now, I've moved over to the School of Electrical and Information Engineering, where I've started my own lab, which is very creatively called the Optical Communications Lab. So I'm going to be talking about interferometric orbital angular momentum mode detection with deep learning, and specifically in turbulence. I did this work with one of my students, Alice, and then two collaborators from within the department. So first of all, what is orbital angular momentum? Let's first look at what is structured light. So if we structure the spatial amplitude and phase of a laser beam, we could call this structured light. And there are many interesting higher order spatial modes, and we need ways to create and measure them. The Laguerre-Gauss modes are very common. This is an OAM mode in the middle here, but we can also add sort of different radial indices, which are called P's, which we're not going to talk about here. There's the Hermite-Gauss modes, which are the square-shaped modes, and then Bessel and Ince-Gauss modes. And there's many types. But like I said, we're going to focus on OAM because they're pretty popular. So orbital angular momentum modes are modes that you would get if you were to take a Gaussian beam and you'd pass it through a spiral-shaped piece of glass. And if you tailored the shape of this glass just right, you know that some of the beam will pass through the thicker part of the glass and some of it will pass through the thinner part of the glass. What this means is that we'll have the spatially varying sort of phase that's imposed on the light as it propagates through, and you'd also then get an amplitude that looks a little bit like this donut here. OAM modes are cool because they're all orthogonal to each other. So we can define them using the topological charge or azimuthal index L, and an L equals 0 would just be a Gaussian mode. But then as we add more and more twists, not only does the beam get bigger, but it also gets this sort of different spatial phase. And they are orthogonal, which means we can add them together with the same wavelength and the same polarization, and we could then split them apart again at some later point if we wanted to. And this is useful because if we wanted to do optical communications with this, we could do something which we could call OAM modulation. This is just one use case for it, of course, but it's the one I'm interested in. So let's say we define an alphabet, and if we have two binary bits, which means we have 4 different combinations, we could assign each of these pairs of bits to a different OAM mode. For example, a -2 would be 0, 0, and this 1, 0 would be L equals 1. And we could take our sort of TikTok cat video and split it into the bits and then transmit a sequence of these. For example, if this is what we wanted to transmit, then we know that this first one is L equals 1. We transmit that across the channel. Then we classify it or demodulate it, and we know that's received. And then we send the next 2 bits, and then the next 2, and then the last 2, and there we have our received data, and everything's great. The thing is, it's not always that easy. In a real optical wireless communication system, we have to deal with atmospheric turbulence, unless you're Elon Musk and you're building Starlink, which is then kind of easy. Let's say we have this transmitted L equals 1 mode. Once we've propagated it through atmospheric turbulence, which is the reason why stars twinkle or you see this heat mirage above the fire, but if you're a laser beam, it's always there regardless of whether you can see it with your eyes or not. What ends up being received is something that's slightly aberrated. And when we try to look at what modes are actually in this, we probably see our original L equals 1 mode, but we would see some other modes as well. And this then makes it confusing because exactly which transmitted mode was it? Now, it's not always this nice, neat Gaussian shaped thing. The shape of the decomposition can vary one time step to the next. So is there a way to classify the transmitted mode easily and reliably? First, let's have a look at how we would create this mode. So generally, we create OAM modes using something called a spatial light modulator, or SLM. And this is basically just a digital hologram that can modulate the phase and amplitude of an incoming beam. So if we had an incoming Gaussian beam, we reflect it off the spatial light modulator. What you get would obviously be the 0 order, which is just the reflection with a bit of sort of noise on it. And then we have a bunch of orders. And we program the hologram so that in this first order, we have the mode that we're looking for. Obviously, there's a problem that if we have a camera, we can see the intensity or the amplitude, but we can't actually see the phase. So are we sure that this is actually the OAM mode that we're intending, or is this just a random ring of light? That's a bit of a problem. So what we do, if we wanted to detect this or double check ourselves, is something called modal decomposition. We can use a second spatial light modulator to detect the modes. And what we can do is say, well, if this is what I created, the columns, then what do I measure? And we do this if we took an incoming field and we reflect that off an SLM with a special hologram and put a camera afterwards, then we see that there'll be light at the center pixel if that mode is present, and there'll be no light if that mode isn't present, and all the values in between. Now, if we didn't want to use a camera, let's say we wanted to do a more high-speed system, we could use a single mode fiber just with some sort of photodiode, and we'd achieve much the same thing. So if there was no turbulence, we would see this perfect diagonal. If there was weak turbulence, so just slight aberrations, we would see the diagonal on average, but there'd be a little bit of crosstalk. And with strong turbulence, you can see here we have fairly significant crosstalk. And from one time step to the next, it might not have this nice Gaussian shape. So things are kind of tough. Now, if we only had a camera, because spatial light modulators are kind of expensive, we don't have too many options. Mario Kren, a few years ago, transmitted what they called twisted light over 143 kilometers. What they had not too many options for what they could transmit. So if they transmitted just the actual OAM modes, you could see as the L gets bigger, the mode gets bigger and you get more space. But can you really tell the difference between this L equals 7 mode and this L equals 3 mode? I mean, this could just be a more diverged version of this. So what you do instead is transmit superpositions, and then you get these petal patterns that appear. So a superposition of plus and minus 1, we have these two lobes. A plus and minus 2, we now have 4, and so on. So here's a plus minus 3, there's 6. And all you have to do is count how many are there. And it's not so clear, but you can pretty much make it out, and so could a neural network, and say, oh, well, this must be that superposition. The issue is that you're throwing away half your mode space because you're forced to make superpositions. So what we decided to do was use machine learning and use the camera because it's easy, but somehow not throw away half of our modes. So we used interference patterns to avoid having to make actual phase measurements, avoid having to use a spatial light modulator, but still not throw away half our mode set. And these are what they would look like. So if we had our Gaussian, we would just have a normal sort of interference pattern. And with a shear interferometer, you'd also see something. Now, what I didn't mention was that we used a Mach-Zehnder and a shear interferometer. A Mach-Zehnder interferometer requires a reference beam, which wouldn't be present if you were 143 kilometers away. But with a shear interferometer, you just interfere the beam with itself, which means you could do it over an arbitrary distance. So if we just zoom in here so we can see what these things actually look like, a Mach-Zehnder interference pattern, you can see there's this clear sort of fork structure in the middle. And that's what we're looking for, and you could see it with your eyes as well. You can count how many tines are on that fork, and you could work out what OAM mode is it. With a shear interferometer, it's not quite so clear. You get these strange looking X shapes, and I guess you could learn the pattern as well. But when we put turbulence through it, you see the thing becomes a little bit more distorted. It becomes harder to see what mode it was. And in particular, the shear also becomes a little bit messed up. Now, can machine learning, or in particular a convolutional neural net, be used to figure out exactly which mode this is? So the experimental setup, we have our laser diode. We split off some of the beam as a reference. We then take the other half and we use a spatial light modulator to produce the different modes. We send off some of the light to the shear interferometer to see what it looks like, and then send the rest off to a Mach-Zehnder. And we obviously do this with various turbulence strengths. We use 7 different turbulence strengths. We did 1,000 measurements of each. So we had a data set of 70,000 images. We use 60% of those for the training process, 10% of them for the validation, which is basically testing during the training, and we saved 30% of the data for our final testing. You can see the shape or the structure of the neural net here. I'm not going to go into that. It's basically just a standard ResNet 18 network. But when you give it an input image, it will output which mode did it think it saw. We importantly normalized the beam sizes because we didn't want to classify based on size by mistake. This is a typical thing. We might end up doing that by mistake, and then we wouldn't actually know if what we were doing was looking at the interference pattern or not. So our results are actually excellent, and we had an accuracy of over 95%. You can see this is 95. Both the Mach-Zehnder and shear interferometer all did extremely well, with the Mach-Zehnder doing a little bit better, probably because there were more pixels in the information in the image. If we had a different shear plate and we could make sort of more dense shear patterns, it would probably work just as well. And you can see here these sort of confusion matrices. We have very little crosstalk and it works almost perfectly. Now, just to be sure that we're actually looking at a logical part of the image and not the size, for example, we can plot something called an activation map. And here you can see these colors is where the neural network is actually looking in order to make its decision on this particular image. And you can see it's focused on the center, which is what we'd expect because that is where the fork-shaped pattern is. In conclusion, the image recognition based on interference patterns is very accurate, even in turbulence, and it's not reliant on superpositions unlike all the other work out there. This is cool because we're not throwing away half of our mode space. And the neural networks are classifying based on physically expected part of the image, not just the size of the beam, for example, or the number of petals. In terms of future work, I wonder if this technique could be extended to do a full modal decomposition. We can do a modal decomp if we do a Fourier transform, a little bit of filtering, so it stands to reason that this should be possible, and I'm going to be working on it. But also, importantly, I think the test should be done in real strong turbulence, because this is not necessarily the same as just the single phase screen turbulence which we used in this work. Cool. Thanks very much, everyone. You can see there I am, and this is sort of some of my team. Yeah, and it was great chatting to you. Thanks very much.